Guys, how's it going? We are very close to the end. This is chapter 10, like I said, is it. We won't go any further after this, so I'm going to review some of the questions from yesterday, which are from chapter 10, section section 2. So first I'm going to do from page 669, I'm going to do number 59, and then I'm going to do a separate video for question number 61. And that should really help you guys with the entire activity. So let's jump right into it here. So question number 59 says, who talks more, men or women? Researchers equipped random samples of 56 men and 56 female students from a large university with a small device that secretly records sound for a random 30 seconds during each 12.5-minute period over 2 days. Then they counted the number of words spoken by each subject during each recording period, and from this estimated how many words per day each subject speaks. The female estimates had a mean of 16,177 words per day with a standard deviation of 7,520 words per day. For male estimates, the mean was 16,569 and the standard deviation was 9,108. Do these data provide convincing evidence at the 5% significance level that a difference in the average number of words spoken in a day by all male and female students at the university? Do these data provide convincing evidence at the 5% level of significance of a difference in the average number of words spoken in a day by all male and female students at the university? So basically what they're testing is they took two very large samples, or not very large, two 56 person samples, one of men, one of women, and they basically calculated the average amount of words that the men speak each day and the average amount of words that the women speak each day. And then they want to test if there's a difference between the two populations, men and women. So this, of course, is going to be a 2-sample t-test for population proportions. Population means. We're dealing with means here. Average amount of words spoken every day, not proportions. Okay? Second thing we have to do is let's define our parameters. So let's call M1. We're going to set that equal to the true mean number of words spoken. I'm having a rough day. Spoken per day by women. And then we're going to make M2 the same exact thing except by men, right? And now we should at least let's write down the important numbers for the sample. So if M1 is for women and M2 is for men, then I'm going to make X bar, because remember M1 or mu1 is for populations. So X bar 1 is for the sample of women, and there were, let's see, female 16,177. That was their average per day, 16,177. And their sample standard deviation was 7,520. And the number of people in their sample was 56. So now let's do the same thing for the men. We have X bar 2, SX2, and N2. I know for the men there was also 56 people in that sample. The men on this particular day spoke an average of 16,569 words. 16,569 words. And their standard deviation was 9,108. Okay? So this is all the information that we have about the men and the women from the sample. The next thing we need to do is we need to check those conditions. Okay, here are the conditions. My first condition is, do I have random samples? And I believe it says in here, researchers equipped random samples of 56 males and females. So this was stated. Check. Right? The second thing is, do we have that normal shape in each sampling distribution, which is which we'll know if we're doing means. If we're doing means, was the sample size for each one bigger than 30? And then on the exam, you can actually, if it is, you can write central limit theorem. I have to look up how to spell theorem because I'm a terrible speller. Oh, I was right. Theorem. Theorem. Central limit theorem. All right, we didn't get to talk so much about central limit theorem in class, but central limit theorem basically says that if you, no matter what the shape of your population distribution is, if you take a sample, repeated samples of it of more than 30, central limit theorem says the sampling distribution will be normally shaped, approximately normally shaped. So both samples, N1 was equal to 56, which is bigger than 30, and N2 was equal to 56, which is bigger than 30. So central limit theorem applies to both of these, and that is a check. And the last condition is independence. And I'll know I'll have independence if my sampling distribution, if my sample size is less than 10% of the population. So I got 56 women in the first sample and 56 men in the second sample. So I think this particular set of tests applies just to people at the university. So you would say it is, and you guys know it by now, it is safe to assume blah 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 that 56 men and 56 women is less than 10% of all the men and all the women at the university. Essentially, we're assuming that the university has more than 560 men and 560 women, because 56 is exactly 10% of 560. So as long as that's true, then I have independence and I can check that condition. So good. So the next thing we have to do is we have to state our hypotheses. So remember, the null hypothesis is always going to be that there's no difference between these two populations. So in other words, M1, or the mean amount of words spoken each day by women at the university, is equal to M2, the mean amount of words spoken each day by all the men at the university. And then the alternate hypothesis is going to be that these two values are not equal to each other. So we know that this is going to lead us to a two-sided test. Okay? So this is going to be a two-sided test. So let's scroll down now. We have to calculate our test statistic, right? So our test statistic is going to be equal to x bar 1 minus x bar 2. So we're finding the difference between these two sample averages, and then we need to divide that by the standard error for the combined sampling distribution, which is always going to be equal to the square root of. So remember here for a second, I don't know the standard deviation of of either one of these individual distributions for men and for women. So I need to take the sample standard deviation from the women divided by the women's sample size plus the sample standard deviation from the men divided by the men's sample size. But remember, you can't add, and this is something we talked about much earlier in the year, you can't add standard deviations. You can only add variances. So I actually need to square those top two numbers when I plug them in. Variances always add. You cannot add the standard deviations. You won't get the right answer. Especially because, look, this is already underneath a square root sign. So I need to square those standard errors, or I need to square those sample standard deviations, add them together. Then I can divide by the sample sizes and take the square root. Okay? So let's plug into this formula and see what we end up with. So x bar 1. So the mean for the women was 16,177. 16,177 minus the mean for the men, which is 16,569. 16,569 divided by, under here I have to put the square root of, let's see what the standard deviation, sample standard deviation for the women was, 7,520. So I have 7,520 squared divided by 56 plus, let's scroll up here again, for the men it was 9,108. So I have to do 9,108 squared divided by 56. And if you plug this whole mess into your calculator, what you should come out with is negative 392 divided by roughly 1,578. And I'll double check this number real quick just to make sure, even though I already did it. Negative 392 divided by 1,578 is equal to negative 0.248. Alright, so remember now for a second. We are doing a two-sided test, not a one-sided test, right? So not only do I want to test or find out what the probability of getting a t statistic of negative 0.248 or more extreme, I want this probability, but since I'm doing a two-sided test, I also want the probability that I get a sample statistic that high, a t-statistic that high or greater, okay, because I'm doing a two-sided test. Struggling. I deleted everything. Good Lord. Come back. Okay, there we go. So I'm doing a two-sided test, like I said. So I actually want to know, well, what's the probability that I get a difference like this, and then when I calculate my test statistic, I get either a test statistic that is this low or lower, or this high or higher. Okay. So to find that probability, what I'm going to do is I'm going to use the function t CDF. It's just like normal CDF, except it's for the t distribution. And to do that, I need to tell the calculator the lower bound, I need to tell it the upper bound, and I need to tell it the degrees of freedom. So the lower bound that we're dealing with, let's get this area right here. The lower bound is some really, really big negative number, or I should say really, really small negative number. So negative 1e99 is the closest approximation that we're going to use for negative infinity. The upper bound then is going to be the top of this area on the left up here, so that's negative 0.248. Now the degrees of freedom, this is something that you need to know right now. The degrees of freedom when you do a two-sample t-test for population means is always going to be the smaller of either of the sample sizes minus 1. So in this case, both the sample sizes were the same. They're both 56. So 56 minus 1 is 55. So I'm going to use 55 degrees of freedom. However, sometimes you'll get questions where the sample sizes are different. You're going to pick the smaller sample size and subtract 1, and that's what you're going to use for the degrees of freedom. So I'll do this on my calculator right now. So I see TCDF, if I put in -1E99, comma, negative 0.248, comma, 55, I'm going to come out with an area. So the area that I'm talking about right now is this area. I'm talking about this area right here, and that's going to be equal to 0.4025. 0.4025. Now remember, that's just this area on the left. Well, guess what? This area on the right, because the distribution is symmetrical, and this is just the negative version of this guy, this area is actually going to be exactly the same. So if I want to find the area of getting a test statistic that small or smaller, or this large or larger over here, I can take what I got for the first one and I can just multiply it by 2, and I'm going to get 0.8, what did I get? 0.805. 0.805, right? In other words, what I'm saying is, given that this is true, given that the mean of the females is equal to the mean of males, there is about an 80% chance that we would get a test statistic this low or lower, or this high or higher, purely due to random chance. And now if I'm comparing that to a 5% level of significance, well, 0.805 is much larger than 0.05. So I am going to fail to reject the null. Fail to reject the null that M1 is equal to M2. We do not have convincing statistical evidence that there is a difference between the average number of words spoken by women at this university and spoken by men at this university. All right? So I hope this helps you guys. I know this gets kind of complicated. I am looking forward to finishing the last section tomorrow, and then going back and reviewing. We will review every chapter 1 through 10. The AP test has actually been pushed back a little bit until the end of May. I will have a post about that in a little while with the details on the new format, date, and time of the AP exam. And then we're gonna be reviewing everything for the next basically month after this, chapters 1 through 10. I will post new videos of me doing I'm gonna have to do 1 tail tests and 2 tail tests for 1 sample means and proportions, 2 sample means and proportions. I'll get the whole thing up there, and you guys will be good to go. All right, so I'm gonna post another video about question 61, which relates to this same exact example here. I'm gonna work on that now. Post it in a couple minutes. All right, see you guys in a few minutes.